Let's continue our discussion on the order of a finite group and its element. In this problem, let A be an element belongs to group Z such that the order of this element is n. It means A to the power n will be obviously identity. If any other power else than n gives identity such that A to the power m is also equal to E, this is m and this is n. A to the power m is also an identity. Then this m will be divisible by n. It means this m will be completely divided by n. For an example, let us hold it. There is a group in which we have some elements. Suppose we have two elements, iota and minus iota, and here we are discussing only on a single element. In this problem we are not discussing about the group, we are discussing about the element of group. Let us take this first element I, then the order of this element I is equal to 4, because the least power 4 gives identity, that is 1. Multiplicative identity can be obtained by applying power 4 on this iota. After that, what will be the next power which will give identity, that is 1, which will give multiplicative identity, because here we are taking an example of multiplicative group. Obviously I to the power 5 will not give expected result. I to the power 8, the next will be I to the power 8, which will gives again 1. So here we have to prove that the next power except then order will be divisible by order, will be completely divisible by order. So if you divide this 8 by 4, if you divide the 8 by 4, then you will get 4 to the 8 and remainder will be 0. So this 8 will be completely divisible by the order. So in this problem we have to prove that if n is the order of this element A and m is another power which is also giving an identity, so this m will be divisible by n. Let us start the proving of this problem by using contradiction. In here we are assuming that n is not a divisor of m. It means m is not completely divisible by n. So if you want to divide this m by n, suppose we are taking the table q time, this is q cent, and we get here something, and this division continuously going on, and in last we get the remainder r. If we get the remainder r, then this m is not completely divisible by n, else we will get remainder 0. So the m can be written as nq plus r. For an example, suppose you are dividing 22 by 7. Suppose you are dividing this 22 by 7, then your table goes thrice, 7 3s are 21, and you will get the remainder 1. You can write this 22 in this manner. 22 can be written as, just a second, this 22 can be written as 7 into 3 plus 1. It means divisor into quotient plus remainder. Then you will get dividend. This is dividend and this is divisor. Sorry, you will get divisor. Divisor equal to dividend into quotient plus remainder. So in this case, this m will be equal to n into q. As this 7 is going multiplied with this 3, here this m will go to be multiplied with this q, and you will add this remainder in the resultant, nq plus r. So the nq plus r will be equal to m. Because if you apply this power m on any particular element a, then you will get identity. So this a to the power m, here m can be written as nq plus r, you can break this result into two parts, a to the power nq into a to the power r. Here n and q both are integers, so you can apply here multiplicative commutativity. So nq will be equal to qn, and nq will be equal to qn. Here we have applied. So what? No, commutativity is not necessary here. You can directly apply a to the power n. As n is the order of a, n is the order of a, so this a to the power n will be equivalent to e. And if you multiply this identity a number of times, it means q times, then you will get identity. If you are operating this identity on again on identity and again on identity, then you will get identity. It will not be changed. So this is e to the power q, that is e, into a to the power r, which is equal to a to the power r. So the a to the power m equal to a to the power r. It means m equal to r. If you compare this result, m equal to r. If m and r both are equal, is this possible in the case of dividing? In the case of divide, remainder can never be equal to the divisor, because n is the divisor and this is r. Remainder will be always less than divisor, so which is a contradiction, which is wrong. So our assumption is wrong. It means m is the divisor of n. It means n can divide this m completely. That is, remainder is not allowed here. So the value of r will be 0, because this is the rule. So a to the power r cannot be equal to this identity, because our assumption is wrong, so it will not equal to identity. So we can directly say that this m is divisible by n. I hope students have understood this point. What I want to say, that I am repeating again. In this case, if you compare this a to the power m with a to the power r, then we got m equal to r, which is not possible. Which is not possible. If you look this as dividing wise, then remainder is always less than divisor. But if you are taking as you are considering it as the point of view of group, then because a to the power m is equal to identity, so a to the power r will be also equal to identity, and remainder is always less than quotient. Sorry, this dividend, remainder is always less than this dividend. So we can also write it in this manner, that remainder will be also less than n. This is the rule of divide. So this assumption is wrong. So we cannot take m and n by using this relation. It means this m will be completely divisible by n. Here we are taking the converse of that problem, because the if is included in our statement. It means we have to prove it necessary and sufficient conditions both. In conversely, now we are assuming that n is a divisor of m. It means m can be completely divided by n. So if you want to divide this m by n, if you divide this m by n, then there will be a quotient, and after that you will get the remainder 0. In this case, this m will be equal to nq. So we are taking here m equal to nq. As a to the power m is equal to identity, so a to the power m can be replaced by a to the power nq. So this will be equal to a to the power n, and this will be equal to a to the power m into power q, and this will be equal to a to the power e. This is identity, and into e to the power q, and now e to the power n. sorry, this is E, this is identity, because the value of a to the power n is E, so this is identity, and you can take any power of this identity element, you will got identity. So left hand side is equal to as well as right hand side, so this statement is here, has been verified here. So we can say that if the order of a group is n, and a to the power m is also identity, gives identity, because n is the order of an element, so a to the power n will be also equal to identity. And we can have a power less than the order for an element. In that case this element could give identity, because order is the least power for a element. For that element could give identity. So in this case, if both statements are true, then this m will be completely divisible by this n. In this next theorem, we will prove that the order of this element A, you have a single element A, and if you have the order of this element equal to n. So if you multiply this element A by another element x and its inverse, you can multiply it from right as well as from left, it is of your choice. The order of this element, because here x into x inverse, if we eliminate this A, then x into x inverse will be equal to identity. So these two components will not affect the order of this resultant. It means the order of this complete element here, or this output will be equal to n. So in this statement it is written that order of element A and x inverse Ax both are same, where A and x, these are the elements of group. So as per our statement, we are written it in two lines. In first line, order of A is n. This is the mathematical way to write the order of an element. It means this is the least power which gives identity on applying on this element A. Again, the order of the second element, this is equal to m. Here this is our assumption, and we are taking contradiction here. We are assuming that the order of both these elements are different. So the order of A is n and order of x inverse Ax equal to m. This is our assumption, but we wish to prove that n and m both are equal. In our previous slide, we have written that x inverse Ax, the order of this part is equal to m. It means it will gives an identity. We have written it in our previous slide. What will happen if you take square of this element? Then square of this element will be written as in this manner. Now you can apply associativity on these two elements. X into x inverse, if you apply inverse on an element, then you will get an identity. This A into E, if you associate these two, then you will get again A. So this is A into A, it means A square. So if you apply the square on this complete element, then this square comes here in resultant. So on proceeding this approach in a general manner, then if you apply n power on this complete element, then this n power will comes here. So it can be written as in this manner. As we have written in our previous slide that order of A equal to n, it means that if you apply n power on A, then you will get identity. So A to the power n, this is equal to identity. So here it is E, and if you operate this E on any element, either on x inverse either on x, then you will get the same element. Here we are applying on x, so you will get x. X inverse x, this is again equal to identity. It means x inverse of x, x inverse of Ax, the order of this element is again n. It means n is a power which for which this element gives an identity. So if you follow this statement, then you can write that order of this element x inverse Ax is n. This is the mathematical way to write the order of an equation. So every another power which are giving an identity, then that powers will be or less than order, because for an element order is the least number which gives an identity on applying on it. After the order, any other powers can gives an identity, and that powers will be divisible by an order. So here we have already considered that m gives identity, and here we are writing here n gives identity. So obviously n will be less than equal to m. So this is as per our assumption, because here we are obtaining that n power on this element gives an identity. So here we assume that the order is the least power for an element which gives identity, so other elements will be more greater than this order. But if we follow the question, in question it is written that the order of this element is m, order of this element is m, then this m will be less than others. This m will be less than others. In this case, because n is the order of m, so or if you consider first this case and in last this case. If you consider this case in first, so you can treat as an order, so n will be less than m. And what will be the relation between n and m? This m will be divisible by n, so you can write here n, this is qm. But if you consider this part first, so you can write m is the order of this element and n is another power. So now this n is divisible by m. So this n is divisible by m, and you can write here, suppose this is your quotient q1 and this is your quotient q2. Both statement cannot do simultaneously, only accepting one case. Let us suppose you have 8 and you have 4, and you want to write this in this manner, that this 8 is divisible by 4. Obviously you will get the answer 2. And you want to also write that this 4 is also divisible by 8. No, this will be wrong. This 4 is not divisible by 8, while 8 is divisible by 4. If you want this cyclic relation, then it will be true only a single situation, that both elements are equal. It means if you want to write the first element is divisible by second, this is true. And if you want to write that second element is divisible by first, then now it is true. So equation first and equation second both can be true, only a single situation, that m and n are equal. So we can say that the m and n both are equal. That is, the order of an element A and x inverse Ax both are equal. This is very simple problem. In this problem we have proved that the A is an element of order n. Here A is the element of a group and its order is n. So A to the power n, this will be equal to identity. And if you take any prime number and you are taking this prime as power of p, then the order of this part will be also equal to n. It means if you take n power on this, then you will get an identity. So here this is our first statement given in problem. Order of a equal to n, that is a to the power n equal to e. And what will be happen if you apply the n power on a to the power p, then it will be written in a to the power pn. Here p and n both are integers, where p is a prime integer while n is another integer. It may be prime or non-prime. You can apply multiplicative associativity on these numbers, so you can write pn equal to np. If you take an associativity between these two elements n and p, you can take a to the power n, and after that you can apply power p. And we know that a to the power n, which is equal to identity, and you can apply any power on identity, then the result will be always identity. So the order of a to the power p is also n, and where p is a prime number. In case of any difficulty, please contact me. Thank you.